Hi everyone, I'm Mikhail Volkhov, and this is a paper called ZSwap, implementing non-interactive multi-asset swaps on top of Zcash. So we start from a very basic separation between public and private ledgers. So in the public world, you usually have some kind of transactions that send money in clear. And then if party A wants to send something to B, it needs to reference the transaction, the previous one that sends money to A from C. And then it attaches some kind of a signature to prove that it authorizes this spend. If you want to do something like that in the private setting, usually it's much more complicated. So you have all the values inside the transaction hidden by default, and then A only sees its own transaction, and then when it wants to send something to B, B will only see its own transaction, but not the previous input. So to reference the previous transaction, you need to attach some kind of a proof or a signature, a zero-knowledge proof in case of Zcash, or a ring signature in case of Monero, which will hide the way money was flowing into this account, into the last account. This difference is very visible if we're trying to build some kind of centralized finance solutions. In the public world, where we have smart contracts, for example, take Ethereum or Cardano, on these platforms, you can build lots of different tools like automatic market makers, exchanges, lending platforms, investment stablecoins, etc. If someone wants to implement something like that on private cryptocurrencies, on private ledgers, again, it's much more complicated, not just because of inherent limitations, but because of just the practical considerations. If you want to add some kind of anonymization tool on top of Cardano or any public chain, essentially, like a Tumblr or a Mixer, it's often trusted anonymous or it requires a lot of setup. If you want to add smart contracts on private chains such as Zcash or Monero, it is quite challenging. It's just quite challenging. And private smart contracts, theoretically possible, even practically possible, but still not being implemented on any big scale because of many practical problems with their implementation. So what we're trying to solve here, what we're trying to attack here, is this area of hybrid solutions where we have private cryptocurrencies, but we add very basic multi-token functionality here to them. So examples of those are, for example, SwapCT. This is a paper by our co-author Felix Engelmann, presented at PET 21. So this adds swaps into Monero, essentially. And then we also have, for example, these two categories of solutions, so called user-defined assets on Zcash or multi-asset shielded pool, MASP, on Tezos and Anoma. And these are pretty much the same idea of how do you add multiple tokens on top of Zcash-like cryptocurrency. So we believe that these solutions can be a very solid basis for later interacting with private smart contracts. So they are very necessary to get right. And in this area, we present our work called ZSwap. It's a cryptocurrency mechanism, very much Zcash-like. It's an extension of Zcash, which presents multi-asset atomic swaps. So multi-asset means that we add types into the nodes. So we have a node, like a banknote, that holds the value and also the type. So you can represent many different types in the vein of ERC20 smart contracts. This formalizes MASP. So we do provide a rigorous analysis of MASP. And atomic swaps means that whenever two parties have some coins, so this person on the left has £5, and the person on the right has €4, and they can swap that atomically. And we realize the swap by essentially allowing merging transactions together, non-interactively. So how do we do that? Let's start from something very simple. Let's start from Zcash sapling. We will only cover sapling if not said otherwise. So in Zcash, we have these two main building blocks, I would say they're called nodes and nullifiers. So nodes are these things containing values. And from a node, if you own the node, if you have the secret key, you can derive using PRF a nullifier. And these two things are unlinkable. If you see a nullifier of someone's node, you cannot know what node it contains. So now Zcash maintains two structures: commitment tree, so a tree of commitments of nodes, and then set of nullifiers. Whenever a transaction comes that wants to spend some coins and output some coins, it has a set of input nullifiers and set of output commitment nodes. And so in the end, when transaction is verified, nullifiers go to this set of nullifiers, and the commitments go to this first set of commitment trees. Into the commitment tree. So if nullifiers prevent double spending. So if nullifier is present here, it means that the commitment was already, the node was already spent. To prove that everything works, that the nullifiers are correctly formed and the commitments are correctly formed, Zcash uses NIZICs. So we have a NIZIC, in sampling we have a NIZIC per input, NIZIC per output. So the input NIZIC says that the input nullifiers are correctly formed from some nodes in the Merkle tree, and output NIZICs say that the commitments are just correctly formed. But one thing that is not solved by NIZIC directly is the balance. So how do we make sure that the values inside this input nodes and the values inside output nodes do balance? So input values minus output values is more than 0. So again, in Zcash, it's solved by adding commitments, homomorphic commitments. So this is our nullifiers and commitments of nodes, and we add these value commitments inside here. So each proof contains each node contains a value and the randomness on each side, and then the commitment is just h to the value and g to the r. And as you may see, if you have commitments to all these values on the left and the right, individual ones, if you multiply everything on the left and divide by everything on the right, so this value, you will get a commitment to 0. If everything balances, it's commitment to 0 with this joint randomness r. And then what Zcash does is that it says we have this joint randomness r, and we have this g to the r. So this is a kind of a binding secret key, and the right thing is binding public key. And Zcash provides a Schnorr signature, essentially, the signature sigma on the whole transaction, proving the knowledge of BSK with respect to BPK. BPK is public, BSK is secret. This is how they solve it. So our thinking is, what happens if we just open this value r and we don't try to put it inside Schnorr, inside any non-interactive zero-knowledge proof? So the answer is, we get balancing, so we still achieve balancing, and we achieve some binding. So we don't achieve full binding, but we achieve exactly the type of binding we want to get for swaps. Transactions can be merged, so you can have two transactions, you can merge them together, so all the inputs concatenated and all the outputs concatenated, but you can't split them apart because you don't know the individual randomnesses which you need to split your transaction into. So the first thing that we change is the commitment scheme, the value commitment scheme. We add types into it. So now the type is hashed first, and this hash of type is the new base age of type. We use different bases for different types. This is how we arrive at this vector Pedersen commitment scheme with a very interesting homomorphic property, such that different types produce different bases, and so the values of different types are not summed together. But the randomness, joint randomness, is still the same as in standard Pedersen commitment scheme. To achieve balancing with this vector Pedersen commitment scheme is easy as it was before. Essentially, we have still these values, but now also types, and the commitments to typed values. And then, as before, we just take a product of all the inputs and divide by the product of all the outputs, and we get a commitment to 0. It's a vector, so vector of 0 for different types, and this joint randomness r. The difference is that the r is now part of the transaction, and then we just open it, as we said before. The ZSwap transaction comprises of the basic bits, nullifiers, commitments to the output nodes, zero-knowledge proofs, and this vector Pedersen commitments. But these vector commitments and circuits are very much like in Zcash, so we ignore it for now. This is not very interesting. What is interesting is this open randomness, which allows us to merge and split things, merge but not split things. And then we have this imbalance per type. So imbalance per type is just an open set that maps types to the imbalance. For example, if I have an unbalanced transaction, so it's a standard transaction with a non-zero imbalance, it sells some nodes, sells some coins of type green, it receives some coins of type red. Its imbalance is 5 for green and -3 for red. If transaction is finalized, is balanced, its imbalance is 0. So we get to the swap mechanics now, which is very important. So how do we swap things in ZSwap? For example, A creates an offer. It's an unbalanced transaction from A to A. A wants to sell some green and receive some red. So it creates a transaction, it has this imbalance, public. B does the same but with different values, the opposite values, for simplicity of the example. Then these two offers are sent to anyone, this merger, M, and anyone who sees these two transactions can essentially merge them together into one transaction. And when you merge transactions, you erase information about their imbalance. So this transaction in the end is exactly just as the basic Zcash transaction. It doesn't have any imbalances. It fully hides all the values inside. And this is then sent to the blockchain. There are different ways that you can that the user A can send this offer to different parties. So for example, A can try to swap some funds with B by sending an offer directly to B, and then B creates its own offer, it matches, and then it merges transactions together, and sends it to the blockchain. At the same time, there might be a party called matching service that collects lots of different offers, and then it just merges them all together. Maybe it also implements some kind of additional mechanics on, interacting with users and telling them what is happening to their offers. And so in the same way, it is exactly like an exchange platform where you see different offers and then try to match those which can be matched. So additionally to this, we also argue that informally, that this is a minimal trust implemented that is necessary for exchange, because you cannot exchange funds without revealing at least the imbalance of it. So the system gives a flexibility over how and whom does it trust in exchanging things, but essentially A cannot reveal less than what it reveals for now in the offer. Additionally to this, M can collect fees, so M can always add an additional fee output to the transactions and collect some money for its service. And then it is also possible for A and B and other users to cancel offers. So this works quite flexible in that respect. It's very basic but very flexible. We prove system secure in the standard model. In the game-based setting, essentially we have properties like anti-theft, which is we can merge transactions but not split them. We have balance, which says funds are secure, so you cannot spend funds that are not yours, essentially. And then privacy, that you cannot see what happens on the blockchain, kind of in this indistinguishability notion. And finally, performance of our system is very close to the basic Zcash, so it's quite efficient in that sense. This table compares ZSwap with our implementation of sapling and the basic sapling. And you can see, for example, for spending proofs and outputting proofs, and so for generating spend and output proofs and verifying them, the amount of time spent is pretty much the same. Merging transactions and creating them is extremely cheap. And then the only difference that is noticeable is creating and verifying commitments, but that's just because a Python commitment scheme is a bit more complicated. But the overhead is still very small. And overall, the overhead compared to Zcash is quite minimal. And that's pretty much it. Thank you.